Technical document version management system based on large language models. Abstract analysis of technology documents is a crucial part of the design and verification process, since manual analysis requires significant effort from the engineers. Automation using natural language processing techniques is a promise in the direction of the efficiency improvement. This research showed the utilization of the information from the previous version of the document to increase the overall performance of the automation tools. The proposed method is based on the two models, that is, a sentence embedding for existing requirement detection and the ensemble of large language models, which recognize the new requirement. As a result, the combination of the algorithms give an increase in an F1 score comparing to the existing works, 0.901 and versus 0.754. Furthermore, the proposed approach works with the requirement of the varying length and takes the context in a more flexible way. Introduction. Development of any technical system is based on requirements which are implemented by the designers and thoroughly examined by the verification engineers. At the same time, requirements are based on different kinds of technical documents. According to the IS 01.110 standard, there are various types of technical documents: patents, specifications, data sheets, and a test method as manufacturing standard, system architecture, system design, and etc. Nowadays, natural language processing (NLP) methods are becoming ubiquitous for the text processing and analysis tasks. Several works have shown the requirement for software and hardware development tasks can be automatically extracted with a decent accuracy, more than 80%. However, the existing approach do not take into account the previous version of the document for and analyze the limited and fixed amount of text, for example, sentence or paragraphs. There are also large language model-driven approaches based on the prompt engineering techniques. Nevertheless, as shown in the figure 3, that even very large generating models perform less successful if it was not trained within the specific domain. The proposed technique is a two-stage algorithm. First, it compares the requirement from the previous version of the document to the newer version of the text requirement with the same text and slightly modified ones based on the sentence embedding technique. Second, it applies to an ensemble of LLM-based classifiers to detect new requirements. This approach allows detecting 100% of previous existing requirements and around 80% of the new requirements, which increases the overall accuracy up to over 90%. Chapter 2 is the proposed approach. A. Dataset description. The M-PHY 4.1 specification has been analyzed manually for the purpose of verification by extracting the requirement and designing the test environment to check the correctness of the protocol operation. As a result, the specification has been split into 219 pages of the text consisting the 4,629 sentences. 772 of them are related to the requirement and the 3,857 are not. An example of the data extracted from page 24 is shown figure 1. Since the majority of the technical documents are represented in the form of the PDF file, the parsing process is challenged due to the difficulty of extracting different types of information, that is, text data, images, tables, and lists, and footnotes, and etc. This process can be simplified by converting initial PDF file info star.docc the format by using Adobe tools or openly available Python libraries, for example, PDF2 DOCX. The DOC file can be parsed in an easier way because it is stored in the XML-like format, which makes parsing and processing simpler. To parse the M-PHY 4.1 specifications, the specification file has been converted to the star DOC file .docx format using PDF to DOCK and further analyzed using an unstructured library. Unfortunately, the current way of the parsing does not always provide 100% quality and requires manual review to confirm the parsed text blocks are correctly split into sentences, and the content of the figures, tables, and footnotes is separated. Then the text elements are combined with the labels into a .json format as shown in Figure 1. The different technical documents are typically edited in various ways depending on the preference of the publisher. As a result, it's almost impossible to design a universal parsing algorithms handling all the issues that arise during the document processing. Thus, currently the manual post-processing is unavoidable practice. Specification of the M-PHY, the version 4.1. These converted to the like this. Figure 1 on example of the data extraction from M-PHY 4.1 specification, page 24. So to find for the validation process purpose, the M-PHY 6.0 specification has been used. The specification has been parsed in different way, that is excluding headers and footers text, section and subsection titles, and etc. into 249 pages containing 2,892 sentences. 1,246 of them are requirements and 1,646 are non-requirements. Structure of the version management system. Consider two versions of the document specification. The first version of the document is X, older version, and the second version of the document is Y. X is older than Y. Right? The block diagram of the proposed method for processing these two documents is shown in Figure 2. Figure 2. Block diagram of the document version management system. The requirement from the document V, X can be extracted with the pre-trained classifier M0 or manually M1. Then the extracted requirements are processed with the LLM, which computes embedding for each atomic part. The same LLM is used for the embedding computation for the contents of the document V. Why? That is the whole content, not just requirement, as they are unknown and need to recognize it. As a result, embedding of the requirement from the document V, the X, EX, and embedding of the atomic part of the document V, Y, the EY are saved to the storage for the embedding, so that the storage can be implemented in different ways. For example, as a vector database. After the preparation step, the embedding from the storage can be processed to determine the class of each atomic part of the document V, Y. V.Y. The two steps should be completed for each embedding vector EY of the newer version of the document. First, vector EY is compared to the vectors of the requirement EX to find the vectors closest to the EY. The similarity matrix can be different. For example, the cosine similarity, as well as algorithms of finding the closest vectors, the approximate nearest neighbor of search. So based on the similarity matrix, the closest vectors get a similarity matrix S, the real number from the 0 to 1, which is compared to the threshold value TH, the real number from the 0 to 1. If the value of the S 1.0 vector EY can classify the as exact match class 0 and T0. If the value of the S is greater than a TH, then smaller than 1.0. The vector EY can be classified as a good match, class 1 and T1. These two classes can be determined without using a classifier. Machine learning models per SE, but can be used as additional data features during the classifier training. If the value of the S is smaller than the TH, the second stage of the proposed algorithm is initiated. That is, the classifier determines the type of the vector EY as having a requirement, class 2, T2, or as 1 without a requirement, class 3, T3. As a result, all The appended part of the newer version of the document classified into 4 types. Class 1, T1 can be used to show the editing differences between the requirement in older and newer version of the document. The quality of the requirement detection highly depends on the classifier performance as it may perform worse than the part of the document it has been trained on. Subsequently, the quality of the classifier can be improved by using a large amount of diverse data extracted from the technical documents. So the C, classifier description. The basic element of the proposed approach is a multi-labels classifier based on an LLM. The structure of the classifier with the sentence context window is shown in Figure 3. Figure 3 is a multi-labels classifier block diagram. If the dataset has an n sentences, the number of data points for this classifier is cell n/s, n over s, then therefore the bigger context window size S is chosen, the smaller dataset is used for the training process. Since the different documents require different sizes of the context window, the multiple K multi-labels classifier are used to form an ensemble model. An ensemble model is based on the K models of different context windows, S0, S1, Sk-1. These models are trained on the same data but split into different number of data points, ceiling n/s0 and ceiling as n/s1 over s1 and ceil as n over sk-1, and correspondingly each model generates the n labels s0 minus label 0, s0, s labels n minus 1, s0, and s minus label 0, s1, s label n minus s1, and the sk1 correspond minus label is sk minus 1, sk minus 1, and the label n1 sk1. Based on the labels values, the ensemble neural network is trained in order to improve the quality of the generated labels. Label 0 is the labels n1, and the structural diagram of the proposed approach is shown in Figure 4. So the Figure 4 is the ensemble models block diagram. Consider the classifier Si. The SII I is greater than 0, equal to greater than 0, or the I equal to greater than K minus 1. Sentences context windowed. If the received cell n over S1 data points, each of the armies contain the SI sentences. If n is not divisible by the SI, the last data point should be obtained by the n minus floor. N over SI is a multi-times the SI sentences with some text. This is not a requirement to make the number of sentences in the last data point exactly SI, or n by k labels from a data set to training ensemble network neural network, which change the weights in order to predict final label values for each sentence based on the k labels provided by classifiers. So as a result, model provides a balanced prediction of the requirement for the document text taking into account context windows of the different size. Section 3, Chapter 3 is experimental result. Experimental description. The proposed method has been tested in M-PHY specification versions as x equals 4.1 and y equals 6.0. These calc documents have been manually processed by the verification engineers as part of the verification design process. The atomic part from both documents have been proposed using a sentence transformer library with the SFR embedding Mistral LLM to obtain embedding vectors. The embedding comparison algorithm had been implemented in 3 ways: quadrant vector database and embedded semantic search from the sentence transformers. Levenshtein distance based on the algorithm. This approach does not require embedding vectors can be applied directly to the strings. The threshold value th is 0.9 for all algorithms. B is classifier training. The basic element of the ensemble model is LLM-based multi-level classifier. In this example, the S-level Mistral 0.1 model has been utilized as the basic classifier. Classifiers with different parameters S2, 3, 4, 5 and 10, no, it's a 90, 95, 10, 100. So the 43 classifiers had been trained into the M-PHY-based data set. 70% training data, 30% is the validation data. Each classifier with fixed hyperparameters has been trained for the 30 epochs using the default Atom optimizer. Beta 1 is 0.9, beta 2 is 0.999. Initially learning rated alpha is 0.00001 and weight decay to decrease the overfitting effect. Each model has been also quantized to 4 bits to fit the size of the GPU memory. The distribution of the F1 scores for the classifiers is shown in figure 5. The classifier performance. The performance of the trained classifier depending on the context window size. As shown in figure 5, the performance of the classifier decreases the increase in the context window as bigger value of the hyperparameters as leads to the decrease in the number of data points in training set. Therefore, classifiers with a smaller context window size usually perform better. Some performance drops, for example S75, can be explained by the poor split into text blocks. So therefore, it's reasonable to use a classifier with the S equal to less than 30, as the number of the data points could not drop under 100 items. So the training time for each classifier is around 2 hours, and it slightly decreased by the 2 to 3% with the increase of the parameters as value. Since the classifiers has different sizes of validation set in sentences, it is hard to assess them by the same measuring. Therefore, the number of erroneously classified sentences within a whole specification is chosen as a metric to compare the performance of a single classifier and the ensemble model, utilizing a couple of the classifier. Since the number of the classifier is relatively large, 43, there is no possibility to compare a possible combination to power 43. Instead, the classifier will combine sequentially. The sentence ensemble model contains only one classifier, S2, and the second, the S2, and the second, the two classifier, S2 and 3, and the third 3, 2S2, 3, 4, and the 43, 43rd and minus 43, S2, 3, 4, 30, 35, 40, and 100. A comparison between the 43 singles classifiers and the 43 singles classifier and the 43 ensemble model is shown in figure 6. So the figure 6 is the comparison between the single classifier and ensemble models, number of models, single classifiers, and ensemble models. So the architecture of the ensemble model is a 5-layer, fully connected network, k-linear input, 1040, 2040 ReLU hidden, and 512 ReLU hidden, and 256 ReLU hidden, 128 ReLU as hidden as a one sigmoid output. The ReLU is a rectified unlinear unit activation function. The ensemble model has a hyperparameters k determining the number of the context windows used as an input. The input for models are probability values generated by choosing the classifier. The model has been trained for 30 epochs using a default Atom optimizer with the initial learning alpha rate alpha 0.001. So the dropout techniques p probability 0.2 for each hidden layer has been utilized to reduce overfitting. The training time even without using GPU is negligible, less than 1 minute, as the proposed model is relatively small. To achieve the negligible the number of errors, it is enough to get from K11 8 errors to K16 classifier 0 errors model. Increasing the number of classifiers to ensemble model does not provide a significant increase in performance. That is, some of the combination may give 1 to 2 errors, but overall the quality is comparable. Unfortunately, the amount of data from the specification is not enough to provide a robust performance on unknown data. The inference of the ensemble model utilizes K as a 15 classifier has been tested in an M-PHY specification version 06, version 60, and the ensemble model version 60. Okay, the ensemble model recognizes 100% of the requirements which are inherited from the M-PHY version 4.1 specification that recognizes only 80% of the new requirement. The outcome of the training process highly depends on the type of the document, its format, the style of the language, format of the tables and the figures, and etc. Thus, the algorithms trained on a type of specification would unlikely perform very well on another type of technical document, as it was shown previously. Siege two-stage method result. The requirement from the M-PHY version 4.1 specification 772 sentences has been factorized using the model for the embedding detection without fine-tuning. The embedding vectors for the whole content of the M-PHY version 6.0 specification 2892 sentences has been also computed based on the two-stage algorithm described in section 2, 3 requirement with the same text, the 550 requirement with a similar text has been detected. The ensemble classifier consisting of the K15 Mistral models to the fine-tunes of the H100 GPUs has detected 569 new requirements. The other 1,770 sentences has been classified as non-requirement. Embedding computation requires around 3 to 5 minutes, and another 15 minutes are required for classification with the ensemble models. The result of the experiment are summarized in Table 1. So the Table 1, the result of the proposed method obtained in the M-PHY specification. So the vector database and the semantic search approaches provide almost the same result. They are based on the same principles. The slight difference in their performance can be explained by a relatively small amount of data, which is more efficiently processed by the semantic search algorithm. The Levenshtein distance based on the algorithm had missed 47 requirements because the string comparison does not take account the semantics of the compared string. The result of the string comparison algorithm can be worse if the amount of data is greater. However, the computational resources are limited. This algorithm can be considered as alternative. The good match requirements T1 are slightly modified the previous specification to the neuron. Some of the examples of these requirements are shown in Table 2 with corresponding changes. And next one, the Table 2 is examples of requirements with insignificant changes. The quality of the good match requirement detection depends on the threshold value th. Therefore, if this value th is smaller, 0.3, the algorithm can be wrongly detect a non-requirement statement as a requirement. On the other hand, the high th values, 0.95, lead to a detection-only exact match-like requirement. As a result, tuning this parameter in a proper way allows avoiding erroneous requirement detection in a newer document if the requirements the original document are correctly identified. So the M-PHY version 6.0 specification has 1,246 requirements, and 553 of them have been detected based on the requirements similarity from the M-PHY version 4.1. Besides, the classifier has detected 569 new requirements as a result. 1,122 requirements has been recognized and improved the accuracy and fixed classifiers, and from approximately 80% of the approximately 90%. Chapter 4 is the use of the proposed method in a verification workflow. The verification process is quite standard and usually based on the specification as a foundation. The modification of the usual workflow is shown in Figure 7. The modified verification workflow. The specifications are usually analyzed by the experienced verification engineers in order to extract requirement. The proposed method targets to replace this stage with an automatic artificial intelligence AI system. The output of the system falls on part of the M-PHY specification is shown in Figure 8. The Figure 8 is the result of the automatic requirement recognition. The requirements inherited from the previous version of the specification are highlighted as a dark blue, T0, exact match, and purple, T1, good match. The rest of the requirements are highlighted with the color from the yellow, high probability of the being requirement, that is from 0.5 to 1.0, to orange, medium probability, that is from 0.2 to 0.2 to 0.5, and white, no highlighting the low probability, that is less than 0.2. Based on this modification of the source specification, an engineer checks the quality of recognized requirement, that is confirms of reject proposal up manually. Figure 9 shows one of the proposed requirements which is related to specification, text and manually reviewed by the verification engineer. It can be further linked to the test bench checker and model, and etc. Figure 9 is a requirement processed with the requirement management system. So at present, an engineer needs to decide what best way to cover the extracted requirement is. Based on the current state of the natural language processing, it's possible to provide a suggestion of some initial draft on the test benches. However, the quality of the discussed system highly depends on the quality and diversity of available data. It would be hard to expect good generalization ability from the algorithm trained on one or two full-text specifications. Furthermore, the manual processing of the 100-gauge technology document requires a significant amount of time and qualified verification engineer. The cost of this time may exceed the cost of some automation of the verification process. However, since the specification analysis is avoidable during the verification IP development process, the input generated by the machine learning models may improve the performance of requirement identification. Decision on the choice of verification environment element, test benches, test group and checkers, models, and etc. Despite the difficulty and automation of technical document analysis, the flow has been tested in a real project using M-PHY as a necessary component. Comparing to the previous verification experience, the LLM-guided process is faster and requires less time for onboarding new members to project. Thus, the long-term target is significantly increase the amount of labeled data, which should exceed tens of thousands of data points extracted from the different kinds of specification and the other types of technical document. Some minor improvement can be achieved by the LLM specification parameters. 5. Conclusion. The combination of the sentences embedded-based searching algorithms and ensembles-based classifier outperform 90% and 80% previous published work. On a relatively small amount of data, there are no concerns that proposed algorithms would suffer the overfitting. However, the bigger amount of various data extracted from a technical document would improve the quality of significantly. As a modern LLM shows the great performance in text classification tasks. It is also worth noting that preparing multiple labels document requiring significant effort from experienced verification engineers, and that is one of the challenges to address. The proposed approach requires the full text of a document, as in an enriched context of varying length. On the other hand, it allows recognizing the non-sequential multiple sentence requirement. Okay, there are so many references. 1, 2, 3, 4. Okay, today I read this paper, the technical documents, version management system, based on large language models from the DVCON 2025. Thank you for your time. See you next time.